calculated the rank above, when we calculated the dimension for the row space, we found that the row space had dimension 3, so the nullity must be 4 minus 3, or 1. So we had better have found only a single vector in the basis set of the null space, and it's this one right here. Great. So last but not least, let's find the null space for the transpose of A. That's the last fundamental subspace. So I've written down, here's the original matrix A again, and here's the transpose of A, the matrix for which we want to now find the null space. Before we do, let's see if we can calculate its dimension before we even calculate it explicitly. So we can do that already because we know that the rank of A transpose, that's defined to be the dimension of the column space of A transpose. That's how we define the rank. But the column space of A transpose is just the row space of A. And the dimension of the row space of A is just the rank of A. So this is actually a very general proof to show us that the rank of A and the rank of A transpose are always the same. Now let's apply our rank plus nullity result, not to A but to A transpose. Applying this result gives us that the rank of A transpose plus the nullity of A transpose is equal to the number of columns of A transpose, which is 1, 2, 3. So, bringing this number over, and solving for the nullity of A transpose gives us nullity of A transpose equals 3 minus rank of A transpose, which is 3 minus 3 equals 0. Well, it's got to be right. I don't see anything that we've done wrong. Evidently, A transpose has nullity 0, which means what? This is, again, the dimension of the null space of A transpose. So what has dimension 0? Well, the 0 vector space has dimension 0. So essentially what we've shown here is that A transpose has a trivial null space. Let's go ahead and calculate it just to make sure that we can back up or double check this calculation. Now, to find the null space of A transpose, we take A transpose, use it as a coefficient matrix, form the corresponding homogeneous system, or at least the augmented matrix thereof, and move down to reduced row echelon form to find this system for reduced row echelon. If we denote our variables for our homogeneous system by Q, R, and S, then we immediately see, using the first, second, and third rows, that we have S equals 0, R equals 0, and Q equals 0. That is an arbitrary vector in the null space, looks like 0, 0, 0, and that's it. In other words, we found that the null space of A transpose is just the trivial subspace consisting of only the 0 vector. And therefore this has dimension 0, as was previously predicted by the rank plus nullity formula used above. Great, so those are the 4 fundamental subspaces of a matrix. They're closely related. I mean, we saw that they were closely related using the rank plus nullity result. But even more so, let's emphasize another relationship between some of these subspaces. Before we state these relationships, it'll be convenient to have one brief exercise. So here's an exercise. Let W be a subspace, or a vector space I should say, which is spanned by M vectors W1 through Wm. These may or may not be linearly independent, but we will assume for the sake of the exercise that W is spanned by these vectors. Then the result is that X is in the orthogonal complement of W if and only if X is orthogonal to each of the Wi. Actually, I'm being a little sloppy here. To say that X is orthogonal is to say that the inner product of X and Wi is 0 for all I. That is, I should be writing this right here in general. Of course, when the vector spaces are in, this just means the dot product, right? So, a word about the proof of this exercise. Well, both directions are relatively straightforward. For the forward direction, if we assume first that x is in the orthogonal complement of w, then the inner product of x with any element of w is equal to 0. In particular, the inner product of x with any of the spanning vectors wi must equal 0. So there's the forward direction. Assuming x is in the orthogonal complement, it must be orthogonal to all of these spanning vectors. And for the reverse direction, let us assume that x is orthogonal to all of the spanning vectors. And we assume that x is orthogonal to all of the spanning vectors. And now let's take an arbitrary element, little w in big W, and we'd like to show that x must be orthogonal to little w. And then we can conclude that x is in the orthogonal complement. So why must x be orthogonal to this thing right here? Well, if little w is in w, and the w1 through wn span big W, then we can write W as a linear combination R1 W1 plus Rm through Wm. And then let's take the inner product of x with this expression. So the inner product of x with W we can write as the inner product of x with the corresponding linear combination of the spanning vectors W1 through Wm. And now we invoke the property of the inner product that it is linear in the first and second variable. So we can split up this sum on the right and factor out all of the scalars R1 through to Rm and write this inner product as a sum of m inner products. And then we invoke our big assumption that x is orthogonal to all of the basis vectors. So this is 0, all of these are 0, and therefore the entire inner product, the entire sum is 0, and therefore x must be orthogonal to w since their inner product is 0. And that's the exercise. X is in the orthogonal complement of w if and only if x is perpendicular to all of the spanning vectors. Now we're prepared to state some very close relationships between the four fundamental subspaces of a matrix that we wrote down earlier. So let's begin or continue by assuming that first that x is in the null space of A. So I've written this equation down. What does that mean? So if this is our matrix A right here, then to say that x is in the null space simply means that A times x is equal to 0. So that's precisely what I have here. I have 0 equals A times x, where I've written A in terms of its row vectors right here. Okay? But the matrix product A times x we see over here is accomplished by taking each row and forming the dot product of that row with this column. So the dot product of the first row with this column gives us this entry, and so on and so forth all the way down the line. The dot product of the last row with this column gives us the last entry. So